Welcome, everyone. Before we dive into the technical depths, I want to start with a question. Have you ever felt overwhelmed by data? Maybe you've stared at a massive spreadsheet or a database with millions of rows and thought, there's got to be a story here, but I just can't see it. That feeling, that tension between having data and understanding it, is exactly why data mining exists. Let's look at this slide. Turning raw data into actionable insight. Those aren't just marketing words. They represent a fundamental shift in how organizations operate. In the 20th century, competitive advantage came from physical assets, factories, land, inventory. In the 21st century, it comes from information assets. But here's the catch: raw data by itself is worthless. It's like having a library full of books written in a language you don't understand. Data mining is the translator. It's the process of extracting meaningful patterns from large datasets. Notice I said large datasets. That's important. The techniques we'll discuss today weren't designed for tiny Excel files with 50 rows. They were designed for the kind of data modern businesses generate every second: a click streams, sensor readings, transaction logs, social media feeds. The goal isn't just to find patterns. It's to find patterns that matter, patterns that help you retain customers, detect fraud, optimize supply chains, or personalize recommendations. In other words, patterns that create value. Let me paint a picture for you. Imagine you're a prospector in the 1849 California gold rush. You've staked your claim and you start digging. For every shovelful of dirt, you're looking for that glint of gold. But here's the reality. You'll move tons of earth, dirt, rocks, clay, debris for every single nugget you find. Data mining is exactly the same. Your raw data, the dirt and rock, is messy. It has missing values, inconsistencies, outliers, and noise. The gold nugget is the insight, a customer segment that's highly profitable, a pattern of fraudulent transactions, a predictor of equipment failure. But here's the profound part: data mining does not create knowledge. It extracts it. The gold was already in the ground. Your job as a data miner is to separate the signal from the noise. This distinction is crucial because it shapes your mindset. You're not inventing reality, you're discovering it. Your biases, your assumptions, they have to step aside and let the data speak. And just like gold mining evolved from panning in rivers to industrial-scale operations, data mining has evolved from simple statistical tests to sophisticated machine learning algorithms running on distributed computing clusters. Now, let's get academic for a moment, but I promise it's worth it. This definition comes from three researchers: Fenot, Shapiro, and Smythe, who were foundational in establishing data mining as a legitimate field of study. Let's read it carefully. Data mining is the non-trivial process of identifying valid, novel, potentially useful, and understandable patterns in data. Every single word in that sentence was chosen deliberately. Process tells us it's not a one-step activity. It's a journey with multiple phases. Non-trivial tells us it requires effort and intelligence, not just running a basic report. And then we have 4 quality criteria that every good pattern must meet. Let's unpack those in the next slide. This is where theory meets practice. When you're evaluating whether a discovered pattern is actually valuable, you need to test it against these 5 criteria. Non-trivial: imagine you analyze sales data and discover that customers who buy more spend more money. That's obvious, it's trivial. A non-trivial pattern might be customers who buy diapers between 6 p.m. and 8 p.m. are 70% more likely to also buy beer. That's not obvious. That's a pattern that requires digging. Valid: this is about statistical significance and generalizability. A pattern is only valid if it holds up on new, unseen data. If you built a model that perfectly predicts customer churn on your historical data but fails on next month's data, it's not valid, it's overfitted. You've memorized the training data instead of learning the underlying truth. Novel: the pattern should tell you something you didn't already know. In the 1990s, retailers discovered that people who bought diapers often bought beer. That was novel. Today, that same pattern is common knowledge. Novelty is context-dependent. What's new for your organization might be well known in another industry. Potentially useful: this is the business filter. A pattern could be statistically valid and completely useless. For example, discovering that people who buy umbrellas are more likely to experience rainy weather. Well, that's just correlation, not causation, and it doesn't help you sell more umbrellas. Usefulness means the pattern enables action. You can change pricing, modify inventory, target marketing, or improve operations. Understandable: finally, humans need to grasp the pattern. A complex neural network might achieve 99% accuracy, but if you can't explain why it made a prediction, regulators won't approve it, executives won't trust it, and customers won't accept it. Interpretability matters. This slide is a reality check. When people say data mining, they're usually referring to step 5 of a 7-step process. The broader framework is called knowledge discovery in databases, or KDD. Let's walk through each step because this is where the real work happens. 1. Data cleaning. This is the least glamorous but most critical step. Real-world data is messy. You have missing values. What do? Delete the row? Impute a value? You have outliers. Are they errors or genuine extreme cases? You have inconsistencies. Maybe NY and New York both appear. Cleaning consumes 60–80% of a data scientist's time. 2. Data integration. Data rarely lives in one place. Customer data might be in Salesforce. Transaction data in your ERP. Website analytics in Google Analytics. Integration means combining these sources into a unified view. This is where tools like Fenot shine. They can pull from multiple sources and align them automatically. 3. Data selection. You don't need all your data. Selection means identifying the relevant subset. If you're analyzing customer churn, do you need 10 years of history, or is 2 years enough? Do you need every transaction, or just monthly aggregates? Selection reduces complexity and improves performance. 4. Data transformation. Now you reshape the data for analysis. You might normalize values so they are on the same scale. You might create new features like average purchase value from raw transaction data. You might aggregate daily data into weekly trends. Transformation prepares data for the algorithms. 5. Data mining. Finally, this is where you apply algorithms, classification, clustering, association rules to discover patterns. But notice, without the previous 4 steps, your mining results will be garbage. Garbage in, garbage out. 6. Pattern evaluation. You found patterns, but are they good? This step applies the criteria we discussed: validity, novelty, usefulness. You might visualize results, run statistical tests, or validate on holdout data. 7. Knowledge presentation. The final step is communication. Dashboards, reports, presentations. This is where insights become actionable. If you can't communicate the pattern, it doesn't exist. So when someone says, "I do data mining," they are really describing their role across all 7 steps. You know, as I was preparing this section on the KDD process, I kept thinking steps 1 through 4. That's where most data projects go to die. The cleaning, the integrating, the transforming, it's essential, but it kills momentum. So I want 90 seconds to tell you about a tool that's been a game changer in my workflow. It's called Fenot. Think of it as an end-to-end analytics platform that's completely browser-based. You know Power BI and Tableau? Fenot is in that family, but with a powerful twist. Here's what makes it different. On a visual canvas, you drag and drop components to build your entire data pipeline. Bring in data from Excel, CSVs, JSON, or connect directly to databases. Fenot automatically creates PostgreSQL foreign tables from your files so you can query everything with SQL instantly. Then, right on that same canvas, you apply transformations, run aggregations, and generate beautiful visualizations, bar charts, line graphs, box plots. You never leave the platform. Think of it as Tableau's visualization power combined with the workflow capabilities of a data integration tool all in one place. Now, if you look at data mining from a technical perspective, it's beautiful because it sits at the intersection of 3 established fields. Machine learning provides the algorithms, the engines that actually learn patterns from data. Decision trees, neural networks, support vector machines. These come from ML research. Statistics provides the mathematical foundation. Hypothesis testing, probability distributions, correlation analysis. These ensure we're not being fooled by random chance. Statistics tells us whether a pattern is meaningful or just noise. Database systems provide the infrastructure. When you're working with terabytes of data, you can't load everything into RAM. You need efficient storage, indexing, querying, and distributed processing. Database systems make large-scale mining feasible. A modern tool like Fenot sits at this intersection. It uses PostgreSQL, a database system for data management, provides statistical functions for analysis, and enables machine learning workflows all in one integrated environment. This slide visualizes those 3 pillars. Let's give each one a concrete example. Statistics gives us concepts like p-values and confidence intervals. When you run an A/B test on a website, statistics tells you whether the 2% improvement in conversion rate is real or just random fluctuation. Machine learning gives us algorithms like random forests and gradient boosting. When Netflix recommends a movie, ML algorithms are matching your viewing history against millions of other users to predict what you'll like. Database systems give us technologies like indexing and query optimization. When Amazon processes your order, database systems ensure that inventory, payment, and shipping data are all consistent and immediately available. In practice, you can't do serious data mining without all three. Let's get concrete about the kinds of patterns data mining discovers. Each type answers a different kind of question. Classification answers: which category does this belong to? Examples: is this email spam or not spam? Is this transaction fraudulent or legitimate? What customer tier does this user qualify for? Classification algorithms learn from labeled examples and then predict labels for new data. Clustering answers: what groups exist naturally? Unlike classification, clustering doesn't have predefined categories. It discovers structure. Examples: segmenting customers into groups based on purchasing behavior. Grouping news articles by topic without knowing the topics in advance. Association answers: what items occur together? The classic example: people who buy diapers also buy beer. In e-commerce, association rules power product recommendations: customers who bought this also bought. Sequence patterns answers: what behaviors unfold over time? Examples: after visiting the pricing page, then the features page, then signing up for a newsletter. What's the typical sequence? Sequence analysis is crucial for understanding user journeys. Anomaly detection answers: what's unusual? Examples: a credit card transaction from a new location. An abnormal temperature reading from an industrial sensor. Anomaly detection identifies outliers that might indicate fraud, errors, or emerging trends. Regression answers: what numeric value do we predict? Examples: what will next quarter sales be? What price should we list this house at? How many units will this store sell? Regression predicts continuous numbers, not categories. With a platform like Fenot, you could visually build a workflow that pulls transaction data, detects anomalies in real time, and alerts your fraud team all without switching between 5 different tools. Let's clear up some common misconceptions, because I see these mistakes all the time in industry. Not the simple database query running select asterisk from customers where state equals NY is not data mining. That's reporting. Data mining finds patterns you didn't know to ask for. Not just data warehousing, a data warehouse is storage. It's where you keep clean, integrated data. But having a warehouse doesn't give you insights, you still need to mine it. Not a crystal ball, data mining doesn't predict the future with certainty. It identifies probabilities and tendencies. A model might predict a 75% chance of customer churn, but it can't guarantee that customer will leave. Overpromising on predictions leads to broken trust. Not a replacement for human judgment, this is crucial. Algorithms are tools, not oracles. They can be biased. They can miss context. They can find spurious correlations. The 2008 financial crisis was partly caused by over-reliance on flawed risk models. Human judgment, domain expertise, ethical considerations, business acumen must always be part of the equation. You'll hear these terms used interchangeably, but they have distinct meanings. Knowledge discovery (KDD) is the broadest term the entire process we outlined earlier. Pattern discovery emphasizes finding non-obvious relationships, often used in scientific research. Predictive analytics focuses specifically on forecasting future outcomes, what will happen. Machine learning is the technical engine, the algorithms that learn from data. Big data analytics refers to mining datasets that are too large for traditional tools. Think petabytes, not gigabytes. Understanding these distinctions helps you communicate clearly with stakeholders. If a client asks for predictive analytics, they probably want a forecast, not just clustering, in the right tools. Thank you for your attention.